NASA, meanwhile, has successfully averted a big problem. Its engineers had sent a wrong signal to Voyager 2 and had lost contact for nearly about 10 days.
Engineers sent a wrong signal to Voyager 2, and now the space probe is on its own at a distance of 20 billion kilometers.
Launched by NASA in 1977, Voyager 2 is one of humanity's most remarkable achievements in space exploration. Over 4 decades after its launch, the spacecraft continues to transmit data as it travels through the vast expanse of space. What did it witness for the past 4 decades? The human quest for knowledge and hunger for more about the solar system and the universe continues because Voyager 2 has no plans to stop quenching humanity's curiosity. Double buckle up, because we're taking off to the edge of the solar system. Crossing the Heliopause. Let's talk about the heliopause in the simplest of terms. The Sun creates a bubble around itself called the heliosphere, which is filled with charged particles called the solar wind. These particles travel far into space, but eventually they meet particles from outside the solar system, the interstellar medium, which comes from stars and other celestial sources. The place where the solar wind stops being strong enough to push against the interstellar medium is called the heliopause. It's like the edge of the Sun's bubble. In November 2018, Voyager 2 became the second human-made object to cross the heliopause, following its twin, Voyager 1. The heliopause marks the boundary where the solar wind, charged particles emitted by the Sun, collides with the interstellar medium, the matter that fills the space between stars. As Voyager 2 crossed this boundary, it detected a sharp drop in the density of solar wind particles and a corresponding increase in interstellar particles. This confirmed that the spacecraft had exited the heliosphere, the bubble-like region dominated by the Sun's influence. Plasma density measurements. One of Voyager 2's special tools was still working when it crossed the heliopause. It measured the plasma, or electrically charged gas, in space. Voyager 2 found that the plasma in interstellar space was denser than the plasma inside the heliosphere. This was a big discovery because it helped scientists understand more about the environment outside the Sun's influence. Unlike Voyager 1, Voyager 2's plasma instrument was functional when it crossed the heliopause, allowing scientists to gather direct measurements of plasma density. Voyager 2 recorded a significant increase in plasma density, indicating that the interstellar medium is denser than the solar wind. This data helped refine our understanding of the transition zone and the interaction between the heliosphere and interstellar space. Magnetic field observations. Cosmic rays are high-energy particles that come from exploding stars and other powerful events in the galaxy. Inside the heliosphere, the Sun's solar wind acts as a shield, reducing the number of cosmic rays that reach us. Once Voyager 2 crossed the heliopause, it detected a lot more cosmic rays, showing how the heliosphere protects everything inside it, including Earth. Voyager 2's instruments also measured the magnetic field at the edge of the solar system. Interestingly, the spacecraft observed that the direction of the interstellar magnetic field was similar to the Sun's magnetic field, suggesting a level of interaction between the two. This finding challenged some existing theories about how the Sun's influence ends and how interstellar space begins, providing new avenues for scientific exploration. Cosmic rays and energetic particles. As Voyager 2 crossed into interstellar space, it observed a dramatic change in the behavior of cosmic rays, high-energy particles originating from outside the solar system. Inside the heliosphere, the solar wind partially shields the solar system from cosmic rays, but beyond the heliopause, Voyager 2 encountered a higher intensity of these particles. This confirmed the role of the heliosphere as a protective barrier against cosmic radiation. The boundary's dynamic nature. Voyager 2's observations revealed that the heliopause is not a static boundary, but rather a dynamic and fluctuating region. The heliosphere expands and contracts in response to solar activity, creating a breathing effect. These findings underscore the complexity of the Sun's interaction with the interstellar environment and suggest that the boundary is far from uniform, a window into interstellar space. Beyond the heliopause, Voyager 2 entered interstellar space, where it began studying the properties of the interstellar medium. It detected a cold, dense plasma environment, distinct from the hot, low-density plasma of the solar wind. These observations provide a rare glimpse into the conditions of the space between stars, offering clues about the formation and evolution of the galaxy. What does this mean for us? Voyager 2's journey helps us understand the Sun's protective bubble and how it interacts with the space around it. This knowledge is important for future space missions and helps scientists learn more about the universe beyond our solar system. It's like finding the edge of our neighborhood in the galaxy and peeking into the wider universe. Crossing the Heliopause was a historic moment. It showed that Voyager 2 had officially left the solar system and entered interstellar space. Even though it's billions of miles from Earth, Voyager 2 continues to send back valuable information, helping us understand more about the space between the stars. Voyager 2 crossing the Heliopause is like reaching the border of the solar system and stepping into a whole new world. Its discoveries about the solar wind, cosmic rays, and interstellar space have changed the way we think about our place in the universe. This tiny spacecraft, launched decades ago, continues to inspire us with its incredible journey into the unknown. The discoveries made by Voyager 2 at the edge of the solar system have profound implications for future exploration. They provide a baseline for understanding the interstellar medium and its interaction with stars, including our Sun. These findings will guide the development of future missions, such as the Interstellar Probe, which aims to travel deeper into interstellar space and build on Voyager's legacy. 2 pioneering spacecrafts. By comparing the data from Voyager 1 and Voyager 2, scientists have been able to gain a more comprehensive understanding of the solar system's boundary. For instance, while both spacecraft crossed the Heliopause, the conditions they encountered were slightly different, highlighting the asymmetric shape of the heliosphere. These differences suggest that the heliosphere is influenced by external factors, such as the local interstellar magnetic field and pressure. Voyager 1 and Voyager 2 are among the most extraordinary achievements in space exploration, launched by NASA in 1977 to study the outer planets and beyond. Although they were built with nearly identical designs and shared similar missions, the two spacecraft followed different trajectories and encountered unique discoveries along their journeys. We will unfold the similarities and differences between Voyager 1 and Voyager 2, highlighting their complementary roles in expanding humanity's understanding of the solar system and interstellar space. Both Voyager 1 and Voyager 2 were launched in 1977 as part of NASA's ambitious Voyager program. Voyager 2 launched first on August 20th, followed by Voyager 1 on September 5th. Despite its later launch, Voyager 1 was placed on a faster trajectory, allowing it to reach its planetary targets before Voyager 2. Both spacecraft were designed to take advantage of a rare alignment of the outer planets, which occurs roughly every 176 years, enabling them to visit multiple planets using gravitational slingshots. Voyager 1 focused on Jupiter and Saturn, providing groundbreaking data and images of these gas giants and their moons. One of its most famous discoveries was the detailed observation of Jupiter's Great Red Spot and the active volcanoes on its moon Io, the first evidence of volcanic activity beyond Earth. At Saturn, Voyager 1 studied the planet's intricate ring system and its largest moon, Titan, whose dense atmosphere was of great scientific interest. Voyager 2 had a more extended planetary mission, visiting not only Jupiter and Saturn, but also Uranus and Neptune, becoming the only spacecraft to date to study these ice giants up close. Voyager 2 revealed Uranus's tilted magnetic field and discovered 10 new moons. At Neptune, it captured stunning images of the planet's deep blue atmosphere and detected the fastest winds in the solar system. After completing its flybys of Jupiter and Saturn, Voyager 1 was directed upward, out of the plane of the solar system, to study the interstellar medium. In contrast, Voyager 2 continued on its path through the plane of the solar system to explore Uranus and Neptune. These differing trajectories allowed the two spacecraft to provide complementary perspectives on the outer solar system and beyond. Both spacecraft eventually crossed the Heliopause, the boundary where the Sun's influence ends and interstellar space begins. Voyager 1 crossed the Heliopause first in August 2012, becoming the first human-made object to enter interstellar space. It detected a dramatic drop in solar wind particles and an increase in cosmic rays, confirming its exit from the heliosphere. Voyager 2 followed in November 2018. Unlike Voyager 1, Voyager 2's plasma instrument was still functional at the time, allowing it to provide direct measurements of plasma density. This gave scientists more detailed information about the transition from the solar wind to the interstellar medium. Both Voyager spacecraft carry the same suite of instruments, including cameras, plasma detectors, and magnetometers. However, the functioning of these instruments differed over time. Voyager 1 had its cameras turned off after its planetary mission to conserve power for its other instruments. This meant it did not capture images of its journey through interstellar space. Voyager 2, with its plasma instrument operational during its Heliopause crossing, provided critical data about the density and temperature of interstellar plasma, which Voyager 1 could not measure directly. The Golden Records. Both spacecraft carry the Golden Records, phonograph records containing sounds and images that represent the diversity of life and culture on Earth. These records were designed as a time capsule, intended to communicate with any extraterrestrial life that might encounter the spacecraft. While both records are identical, they symbolize humanity's hope and curiosity for making connections beyond our solar system. Together, Voyager 1 and Voyager 2 have transformed our understanding of the solar system and interstellar space. Their data have contributed to numerous scientific discoveries, from the dynamics of planetary atmospheres to the structure of the heliosphere. They also serve as symbols of human ingenuity and the spirit of exploration, continuing to operate far beyond their expected lifespans. Voyager 1 and Voyager 2 are twin spacecraft that have taken different paths but share the same mission of exploring the cosmos. While Voyager 1 was the first to enter interstellar space, Voyager 2's extended planetary mission and functional plasma instrument have provided unique insights into the outer planets and the boundary between the solar system and interstellar space. Together, they have offered humanity a deeper understanding of our place in the universe, inspiring generations of scientists and explorers to continue reaching for the stars. The pressure on Voyager 2. Voyager 2 has been journeying through the cosmos for over 4 decades, delivering groundbreaking insights about the solar system and beyond. After its historic planetary encounters and crossing into interstellar space in 2018, Voyager 2 continues to send valuable data from billions of miles away. Billions of miles, nearly unimaginable. Despite its age and distance, scientists still have high hopes for what Voyager 2 can reveal as it ventures deeper into interstellar space. There are some of the key expectations and scientific goals associated with this remarkable spacecraft. First is the detailed mapping of interstellar space. As Voyager 2 travels further into interstellar space, scientists are keen to map the properties of the interstellar medium, the matter that fills the vast space between stars. This medium consists of plasma, cosmic rays, and interstellar dust, and Voyager 2's instruments are uniquely equipped to study its density, temperature, and composition. By comparing data from Voyager 2 with its twin, Voyager 1, researchers can build a more detailed picture of the interstellar environment and how it interacts with the heliosphere. Experts expect to better understand the heliosphere's shape and behavior. The heliosphere, the bubble-like region created by the sun's solar wind, protects the solar system from many cosmic rays and interstellar particles. Voyager 2's journey provides a rare opportunity to study how the heliosphere behaves and changes over time. Scientists are particularly interested in understanding the heliosphere's shape, which appears to be asymmetrical based on Voyager 2's observations. Ongoing measurements of solar wind and interstellar particles can help refine models of how the heliosphere interacts with the interstellar medium. One of Voyager 2's key contributions is its ability to measure the interstellar magnetic field. Scientists expect the spacecraft to provide more data on how this magnetic field behaves far beyond the sun's influence. This information is crucial for understanding the broader galactic environment and how magnetic fields influence the movement of charged particles, such as cosmic rays, throughout the galaxy. Cosmic rays, high-energy particles originating from supernovae and other celestial phenomena, are a significant focus of Voyager 2's mission. The spacecraft's location in interstellar space allows it to measure cosmic rays without the interference of the sun's magnetic field. Scientists hope to learn more about where these particles come from, how they travel through space, and how the heliosphere acts as a shield against them. This research could provide insights into the life cycles of stars and the dynamics of our galaxy. Voyager 2 is also equipped to study interstellar dust particles, which are remnants of ancient stars and contribute to the formation of new stars and planets. By analyzing these particles, scientists can gain a better understanding of the building blocks of the galaxy. Voyager 2's observations can help answer questions about the composition, size, and distribution of interstellar dust, offering clues about the processes that shape our universe. The data collected by Voyager 2 continues to inform the planning of future interstellar missions. For example, the Interstellar Probe, a proposed spacecraft designed to travel much further than Voyager, will build on the discoveries of Voyager 2. By studying the edge of the heliosphere and the interstellar medium in greater detail, Voyager 2 lays the groundwork for new technologies and scientific objectives in the exploration of deep space. One of the most exciting aspects of Voyager 2's mission is its potential to reveal the unexpected. From discovering active volcanoes on Jupiter's moon Io to detecting the surprising density of interstellar plasma, Voyager 2 has repeatedly defied expectations. As it moves further into uncharted territory, scientists remain open to the possibility of new phenomena, whether related to interstellar physics, particle behavior, or cosmic structures. Beyond its scientific objectives, Voyager 2 provides valuable lessons about engineering and the durability of spacecraft in extreme environments. With its power and instruments gradually declining, scientists are using Voyager 2 to test how long a spacecraft can operate and communicate in deep space. Surely these lessons will guide the design of future missions that aim to explore even farther. As Voyager 2 ventures further into interstellar space, it carries the potential to reach regions influenced by other stars' stellar winds and magnetic fields. Scientists hope that in the distant future, Voyager 2 might detect traces of these neighboring influences, providing insight into how stars interact on a galactic scale. Voyager 2's journey into interstellar space is far from over. Scientists are eager to learn more about the interstellar medium, the shape of the heliosphere, cosmic rays, and the mysteries of the galactic environment. Despite its age and the vast distance from Earth, Voyager 2 continues to push the boundaries of human knowledge, offering a glimpse into regions of space never before explored. As it ventures into the unknown, Voyager 2 remains a testament to human curiosity and ingenuity, inspiring future generations to reach even farther into the cosmos. On the furthest planets of the solar system. Thanks to Voyager 2, we knew more and much about the last 3 planets, furthest from the Sun. It is the only spacecraft to have visited all 4 of the gas and ice giants, Saturn, Uranus, and Neptune, up close. Although Voyager 2 did not visit Pluto, its discoveries at these distant planets provided invaluable insights into their atmospheres, moons, magnetic fields, and more, shaping our understanding of the solar system. Voyager 2 reached Saturn in August 1981, building on the observations of its predecessor, Voyager 1. It made groundbreaking discoveries about Saturn's complex system of rings, moons, and magnetic environment. Voyager 2 revealed the intricate structure of Saturn's rings, discovering gaps, spokes, and braided patterns within them. These findings suggested dynamic processes, such as gravitational interactions with moons and particles clumping together and dispersing. The spacecraft captured detailed data about Saturn's atmosphere, revealing strong winds exceeding 1,800 kilometers per hour and bands of clouds shaped by powerful jet streams. Voyager 2 observed several of Saturn's moons, including Enceladus, which displayed evidence of resurfacing processes, hinting at potential geological or even cryovolcanic activity. This finding set the stage for later missions that would study Enceladus's potential to harbor life. It confirmed Saturn's strong magnetic field and its interaction with the planet's rings and moons, creating unique auroras. Moving to Uranus, let's discover why it's named the Tilted Ice Giant. Voyager 2 remains the only spacecraft to visit Uranus. Flying by in January 1986, its discoveries revealed Uranus to be a strange and mysterious world. Voyager 2 confirmed Uranus's extreme axial tilt of 98 degrees, causing the planet to essentially roll on its side as it orbits the Sun. This unique orientation influences its weather and seasons, creating extreme conditions. The spacecraft detected a cold, featureless atmosphere composed mostly of hydrogen, helium, and methane. The methane gives Uranus its pale blue-green color. Despite its bland appearance, Voyager 2 observed some weak weather patterns, including subtle banding and small storm systems. Voyager 2 discovered that Uranus's magnetic field is tilted and offset from its center. making it highly irregular. This unusual magnetic structure challenged existing models and suggested a unique internal structure. Voyager 2 discovered 10 new moons and 2 additional rings, highlighting Uranus's complex satellite and ring system. Its observations of moons like Miranda revealed dramatic surface features, including massive canyons and evidence of past geological activity. Voyager 2's flyby of Neptune in August 1989 marked the spacecraft's final planetary encounter. It provided stunning insights into this distant, dynamic world. Voyager 2 revealed Neptune's deep blue color, caused by methane in its atmosphere. It discovered powerful storms, including the Great Dark Spot, a massive storm system comparable in size to Earth, and some of the fastest winds in the solar system, reaching speeds of 2,100 kilometers per hour. Similar to Uranus, Neptune's magnetic field was found to be tilted and offset from the planet's center, suggesting a shared characteristic among ice giants. Voyager 2 observed Neptune's faint ring system, confirming the existence of arcs or clumps within the rings that defy the smoothness seen in Saturn's rings. The spacecraft captured images of Neptune's largest moon, Triton, revealing active geysers erupting nitrogen gas. Triton's retrograde orbit and geological activity suggested it might be a captured object from the Kuiper Belt, offering clues about the solar system's outer regions. Let's get to a missed opportunity. Fired from the list, former planet Pluto. Voyager 2 did not visit Pluto because its trajectory prioritized flybys of the outer planets. At the time of its mission planning, Pluto was considered the 9th planet, but little was known about it. Decades later, the New Horizons mission in 2015 would provide detailed images and data about Pluto, showing it to be a complex world with glaciers, mountains, and a thin atmosphere. While Voyager 2 did not explore Pluto, its discoveries of Triton provided an indirect preview of the icy, distant objects in the Kuiper Belt, which includes Pluto. The data gathered by Voyager 2 at Saturn, Uranus, and Neptune transformed our understanding of the outer solar system. It revealed the diversity of planetary atmospheres, the complexity of magnetic fields, and the dynamic nature of moons and rings. Its findings continue to guide current and future missions, such as the James Webb Space Telescope, and proposed missions to Uranus and Neptune, which aim to explore these ice giants in greater detail. Voyager 2's exploration of Saturn, Uranus, and Neptune provided humanity with an unprecedented view of the outer solar system. From Saturn's dazzling rings to Uranus's tilted mystery and Neptune's turbulent storms, the spacecraft unlocked secrets that continue to inspire scientists and fuel our curiosity about the cosmos. Although it did not visit Pluto, its discoveries laid the groundwork for future exploration of icy worlds at the edges of the solar system. Voyager 2 remains a symbol of human ingenuity, pushing the boundaries of what we know about our place in the universe. Exceeding expectations. Imagine the spacecraft built some decades ago, and still there, after 46 years. Voyager 2 stands as a testament to human ingenuity and engineering excellence. Designed to explore the outer planets of the solar system and beyond, Voyager 2 has far exceeded its original mission parameters. It did, and it continues to transmit valuable data from interstellar space more than 46 years after its launch. Voyager 2 was constructed with durability and adaptability in mind, equipped with cutting-edge, for its time, technology designed to withstand the harsh environment of deep space. Built to endure extreme conditions, Voyager 2 was designed to survive intense radiation near Jupiter, the cold vacuum of space, and the vast distances it would travel. Its resilient structure protected its scientific instruments throughout its journey. Voyager 2 uses a radioisotope thermoelectric generator, RTG, to generate electricity. This system converts heat from the natural decay of plutonium-238 into electrical power, allowing the spacecraft to operate far from the sun, where solar panels would be ineffective. The spacecraft's high-gain antenna enables communication with Earth across billions of miles. Despite signal delays of over 18 hours at its current distance, Voyager 2 maintains contact through NASA's Deep Space Network. Voyager 2 is equipped with 10 scientific instruments, including cameras, spectrometers, and plasma detectors. These instruments were designed to study the atmospheres, magnetic fields, and moons of the outer planets, as well as the interstellar environment. Many of Voyager 2's systems were built with redundancy, ensuring backups were available in case of failure. This has been crucial in maintaining its functionality over decades. Voyager 2's longevity is one of its most remarkable achievements, far surpassing its original mission timeline of 12 years. Several factors contribute to its extended lifespan. The RTG has provided a steady power supply for over 4 decades, though it is gradually losing efficiency. NASA engineers have managed this decline by prioritizing power for essential systems and shutting down non-critical components. The spacecraft's components were built to withstand long-term exposure to space's extreme conditions. Its instruments and systems have continued to function well despite decades of use and the challenges of deep space radiation and temperature extremes. NASA engineers have repeatedly devised creative solutions to address issues as Voyager 2 ages. For example, they have reprogrammed the spacecraft remotely to bypass failing components, optimize power usage, and extend its operational life. By minimizing the use of moving parts, engineers reduced wear and tear, which has contributed to Voyager 2's longevity. Many of its systems rely on electronic controls rather than mechanical ones. Despite being launched in the 1970s, Voyager 2 has received software updates that allow it to perform tasks not originally envisioned. This adaptability has kept it relevant as new scientific questions arise. However, the reality is that it's been there for almost 50 years. Voyager 2 has got its continued challenges and obstacles billions of miles from us. Operating a spacecraft billions of miles from Earth presents unique challenges, and Voyager 2's longevity has been marked by overcoming obstacles. As the RTG's power output decreases, engineers have prioritized powering only the most critical instruments and systems. This careful power management has allowed the mission to continue far longer than anticipated. The increasing distance makes communication slower and weaker. Engineers have improved the sensitivity of Earth-based receivers in the deep space network to maintain contact with Voyager 2. Mechanical and electronic components degrade over time. NASA has relied on redundancy and ingenuity to compensate for aging systems, including reprogramming software to bypass failed components. Decades after its launch, Voyager 2 continues to send back data about the interstellar medium, providing insights into the space between stars that were impossible to obtain from within the heliosphere. The spacecraft's longevity has demonstrated the value of robust design and adaptability in space missions. These lessons are being applied to newer spacecraft, such as the James Webb Space Telescope and upcoming interstellar probes. Voyager 2's success has inspired ambitious new missions, including proposals for dedicated interstellar probes and exploration of the outer planets, such as Uranus and Neptune. As Voyager 2 ventures further into interstellar space, it continues to serve as a symbol of human curiosity and ingenuity. Its ability to operate for decades in the harshest conditions reflects the brilliance of its engineering and the determination of the teams managing it. While its power supply will eventually run out, the legacy of Voyager 2 will endure, inspiring future generations to push the boundaries of exploration. Voyager 2's remarkable engineering and technology have enabled it to exceed its original mission goals and continue exploring the unknown for more than 4 decades. Its longevity is a testament to the ingenuity of its creators and the dedication of those who have managed the mission over the years. As it travels deeper into interstellar space, Voyager 2 remains a beacon of human achievement, demonstrating what is possible when engineering excellence and scientific ambition come together. The search for meaning in the universe. As Voyager 2 travels into the interstellar medium, it raises profound questions about the nature of the universe and our place within it. What lies beyond the boundaries of the solar system? Are we alone? Or is there other intelligent life out there? Voyager 2 may not answer these questions, but its mission fuels our desire to seek them out. Its exploration emphasizes our deep connection to the universe, reminding us that we are made of the same elements as the stars. By venturing so far from Earth, Voyager 2 encourages us to reflect on the purpose of existence and the meaning of our place in the cosmos. Voyager 2 is not just a technological marvel, it is also a profound symbol of human curiosity, ingenuity, and our desire to understand the universe. As it journeys beyond the boundaries of the solar system into interstellar space, Voyager 2 invites us to contemplate our place in the cosmos, our shared humanity, and the enduring quest for knowledge. Let's briefly look at the philosophical impact of Voyager 2 on humanity, highlighting how it has shaped our perspective on existence and inspired generations to think beyond our earthly confines. Voyager 2's voyage into interstellar space offers humanity a humbling perspective on its place in the universe. The spacecraft's images of distant planets, moons, and even Earth itself have underscored the vastness of space and the relative insignificance of our planet in the grand cosmic scale. This perspective challenges us to think beyond national or cultural boundaries, emphasizing the shared destiny of humanity as inhabitants of a small, fragile world. Voyager 2 symbolizes humanity's relentless pursuit of knowledge. It was sent into space not knowing what it would find, yet its discoveries have transformed our understanding of the solar system and the universe. This willingness to venture into the unknown speaks to a fundamental human trait: curiosity. It's the end of the video, but not Voyager 2. It will soar higher and discover more secrets of the solar system. We'll see you in the next one.